This is Group 17, The Sapling Protector, by Miguel Solis, Luke Barlow, Francisco Wilson, and Juan Fernandes. The motivation behind this project is to take care of young plants that often aren't looked after too much. I gave my mom 3 blueberry bushes, and they all died within 3 weeks. And a similar story when I gave her a mini guava plant. So plants require a lot of care, and sometimes the people who are taking care or supposed to be taking care of the plants do not give that care. So in order to mitigate the loss of life of the plant, in order to ensure that more saplings make it out of their baby stage, we wanted to create a device that protects them from the sun, because not all plants want to receive the same amount of sunlight. So our initial ideas were a planetary gear system, a thrust ball bearing. This is the original sketch, and it's not listed here, but the design we eventually ended up going with was the tapered roller bearing design. As can be seen here from the side, through a sliced view, the ring gear is able to rotate around the plant without being able to move side to side. And it levitates off the ground because it can only go down so much before the diameter is too small for it to go down any further. The plan was to attach arms with a solar panel to the moving inner cone/internal gear. This solar panel would rotate around according to the position of the sun. Bearing design material covered in class was in the context of millions of revolutions. So what we learned in this class did not apply necessarily to our type of bearing, because it is going to do one revolution in one day. So it is not the context in which we learned bearing design. Instead, we went for gear ratios. This is the gear ratio for the base. This is the motor that's going to turn the inner gear, the internal gear. And we have a 98 teeth on the internal gear/inner cone, and 20 teeth on the pinion. This leads to a factor of 4.9, a ratio of 4.9, which means that angular speed will reduce by a factor of this much, and torque will be amplified by a factor of 4.9. Next, what we did was key design. We chose a diameter of 0.75 inches or 3/4 inches. And what we did was we converted to millimeters and then chose the corresponding key width and height. So since we were between 17 and 22 millimeters, we had a key width and height of 6 by 6 millimeters. This was engraved into our pinions for the gearbox, which we will see later. And this is our code to calculate key length, because we have the width and the height, but now we need the key length. So applying our load to a stainless steel shaft gave a minimum key length of 0.003 inches, which is really short, but understandable since our load is so small compared to the stainless steel shaft. It is around 3 pounds, the solar panel is, so a stainless steel shaft can handle that forever. And the reason we chose the stainless steel shaft was because its corrosion resistance and durability of the material. The next design was a compliant mechanism, which was just researched on the surface level to make a one-way snap fit mechanism. Can be seen here with the dimensions and the fittings in the assembly. Here are the fittings in the assembly. We used it for the inner cone, the outer cup, and the cage, the roller cage. And for the gear ratio of the box, as mentioned earlier, we had 17 teeth for the pinion and 34 teeth for the main gear that's going to be attached to the shaft, the one that had a key design in it. And this reduces the angular speed by a factor of 2, and increases torque by a factor of 2. For the FEA analysis, we had a simple beam with two fixed supports on both sides. The reason it was like this was because most of the time our machine is going to be stationary. It's not going to be moving. It's going to be moving very slow according to the position of the sun. So most of the time we have a static load, and since our load is so small, this gave us a very small deflection, maximum deflection. For the sustainability analysis, we first converted everything to wood just to see where we would go, and our carbon our carbon, energy, air, and water footprint decreased by 98%, but our costs went up by 1,500%. And this is possibly due to the complex geometry, and since wood isn't typically used for machines, I imagine there's some type of cost associated with making those complex parts. So we made a compromise. We chose a ceramic base, which is still eco-friendly to the environment, still environmentally friendly, and it has great weather resistance, hardness, and this makes it an ideal candidate for the job. The weighted inner cone increased costs but reduced all footprints by over 80%. It was the main cause of our footprint decreasing. And the gears, shaft, and rollers were made of chrome stainless steel due to its resistance to corrosion and toughness. Since they are always going to be in contact and going to be moving, and are going to be under the most load, these were made to stay as chrome stainless steel. Now, looking at cost analysis, on the left here we have the section for the non-ideal project, which was constructed from PLA entirely. And although it was constructed from PLA entirely, it only made up 54% of the cost. As we can see here, the total cost for PLA involved in the project was $266, around there. And the total cost in general, the entire project, was $501. This is because the rest of the money was taken up by the other items that were involved, mainly electronics such as batteries, motor drivers, wires, Arduinos, etc. If this was to become a viable product, then we would have to sell it around an $800 price tag to ensure that we make some sort of profit on this. And this is further discussed in the next slide. On the right-hand side, we have majority of this report is irrelevant to the cost analysis and has to do mostly with the sustainability. But what I want to focus on is down here. Here we see that I enlarged this photo right here to see that the difference in price versus this is the $677 is for all cedar for the material, and the $559 is when we diversify into aluminum, cedar, and stainless steel. Looking at the cost analysis, we see that for the PLA version, our sale price is around $800. Cost of materials is around $600 from experience, and this is assuming that our sales increase by a factor of 1.5 times each year. This gives us a net present value of around $22,000, which is greater than zero, which means it's viable. Now, if we look at the realistic ideal approach to making a product using cedar, aluminum, and stainless steel, we see that the sale price has to be around $2,500 because this is assuming cost of materials is around $600, which we previously saw in SolidWorks sustainability feature. And this is assuming that the materials is to be 30% of total cost, which is a conservative estimate. And this also assumes that sales increase by a factor of 1.5 each year. And right here we see that we get actually a lower net present value than when using the PLA. For future improvements, we can do several different ones. We can make a cover to shield the rollers, pinions, and inner cone from natural elements, ensuring that our product lasts at least 5 years, which is the goal. Another thing we can do is build fins, which is seen on the right here. It's an example of heatsink. Similarly, we can build fins on the parts that contain motors and batteries, which prevents overheating and breakdown of the electrical system. Another thing we can do is make the arms 2 feet instead of 1 feet because that was what was planned. This also allows for a larger area that is covered by the solar panel. You can also create a circular ring, a base, that goes underneath the outer cup. That way it also acts as a case for the inner cone as it sits under it and protects it from being rubbed by grass or uneven terrain. This also ensures that uneven terrain never affects the product, and so that the inner cone can run smoothly. And then another feature improvement is to minimize cost and weight by doing more material cutouts or windows, which is seen here on the right. Doing this, when putting this into the slicer software from Bamboo Lab, we were able to reduce weight and cost of the inner cone by 11%. And we can redesign the arms so that the shaft length is shorter and coming out parallel to the hole instead of at an angle, and even add a cable reel system so that the entire project or the entire machine is under one Arduino or microprocessor, microcontroller, or one battery. Here I'm just going to label and give you guys an idea of where everything is. So right here we will start with the gearbox. The gearbox is a 2-to-1 gear ratio, and we have 2 motors on it, so that I can output enough torque to turn this solar panel. Here is the base motor, which, as you can tell, a little bit of a problem is that it doesn't go deep enough, so it is not fully meshed how it should be. But in order to solve this problem, we can either dig a hole or decrease the height of this base motor. Since it's a tapered roller bearing, as we go down further, the diameter shrinks. So if we fix the diameter for the inner cone or internal gear, and we also fix the diameter of the outer cup, then eventually it will not be able to go down any further. The problem that we encountered is that there is not enough space between the inner cone / internal gear and the ground. This is due to the rough terrain. So as we can see here, we have a nice space between, but as we move along the terrain, it gets tighter and tighter. This is not due to the unevenness of the inner cone, but rather the unevenness of the terrain itself. So in order to compensate for this, a future consideration, future development would be to introduce a base below everything that is sort of a ring, and it flattens everything out. That way it's always flat and there's no interference between the grass or other debris. As we can see that at this position, the plant would ideally first off have a bigger solar panel to cover the plant when the sun's right above. And this is the position it would be at, and then it would be able to rotate like this to cover the plant accordingly, and it would rotate the base as well. So, okay, let's get this thing started. So first, I will start off the solar panel. I will preface this by saying that we don't have everything autonomously controlled as ideally it would be. It would ideally take in sunlight from the sun and then move accordingly, position itself accordingly. Right now, we just have a proof of concept that it moves and that the gears work. So, mind you, this is not how it's going to be ideally. And the same thing goes for the base motor. We have it at a constant speed, whereas ideally it would be moving according to the position of the sun. So here goes first the solar panel. And then in conclusion, the sapling protector is a great tool for those who are trying to take care of little plants, and grow them themselves, but perhaps don't have the time to take care of them or are constantly going away from their home. The sapling protector is an eco-friendly device and machine that helps life grow more abundantly and helps people take their gardening to the next level. Thank you for watching. Here I'm just going to label and give you guys an idea of where everything is. Here we will start with the gearbox. The gearbox is a 2-to-1 gear ratio, and we have 2 motors on it so that I can output enough torque to turn this solar panel. Here is the base motor, which, as you can tell, a little bit of a problem is that it doesn't go deep enough, so it is not fully meshed how it should be. But in order to solve this problem, we can either dig a hole or decrease the height of this base motor. The reason it can't go downward anymore is because